Hi, everybody. Glad to see you again. And let's start our astronomy course. Okay. So today we have lecture number 7, atoms and starlight. During today's lecture, we will be studying about the atoms and what did starlight mean. In the last lecture, you heard how telescopes gather starlight and how spectrographs spread the light out into spectra. Now you are ready to see what all the fuss is about. Here you will find answers to 4 essential questions. What is an atom? And how do atoms interact with light? How does an atomic spectrum form? And fourth, what can you learn from a spectrum? And this lecture makes a change in the way you will look at nature. Up to this point, you have been thinking about what you can see with your eyes alone or aided by telescope. In this lecture, you will begin using modern astrophysics to search out the secrets of the stars that lie beyond what you can see. The analysis of spectra is a powerful technique, and in the lecture that follows, you will use that method to study planets, stars, and galaxies. And when an object emits light, the atom in that object can leave their mark on the light. By understanding what atoms are and how they interact with light, you can decode astronomical spectra and learn the secrets of the stars. To think about atoms and how they interact with light, you need a working model of an atom. In previous lectures, you used a working model of the sky, the celestial sphere, and in this lecture, you will begin your study of atoms by creating a model of an atom. Your model atom contains a positively charged nucleus at the center, which consists of 2 kinds of particles. Photons carry a positive electrical charge, and neutrons have no charge, leaving the nucleus with a net positive charge. The nucleus of this model atom is surrounded by a whirling cloud of orbiting electrons. Large mass particles with negative charges. Normally, the number of electrons equals the number of protons, and the positive and negative charges balance to produce a neutral atom. Protons and neutrons each have masses about 1840 times that of an electron. Imagine how large, right? So most of the mass of an atom lies in the nucleus. Even though a single atom is not a massive object, a hydrogen atom, for example, has a mass of only 1.67 times 10 in power minus 27 kilos, about trillion over gram. An atom is mostly empty space. To see this, imagine constructing a simple scale model of hydrogen atom. Its nucleus is a proton with a diameter of about 0.5 zeros and 16 nanometers. or it's 1.6 times 10 in power minus 15 meters. If you multiply these by 1 trillion, 10 in power 12, you can represent the nucleus of your model atom with something about 0.16 centimeters in diameter. A grape seed would do. The region of hydrogen atom that contains the virulent electron has a diameter of about 0.4 nanometers or 4 times 10 in power minus 10 meters. Multiplying by a trillion increases the diameter of about 400 meters, or about 4.5 football fields laid end to end. Let's look at this figure, please. And when you imagine a grape seed in the middle of a sphere, 4.5 football fields in diameter, you can see that the atom is mostly empty space. All these light blue colors is empty space. Now, you can understand a common misconception. Most people, without thinking about it much, imagine that matter is solid. But you have seen that atoms are mostly empty space. The chair you sit on or the floor you walk on are mostly not there. When you study the death of stars in a later lecture, you will see that what happens, to a star when most of the empty space gets squeezed out of its atom. There are over 100 chemical elements. Which elements an atom is depending only on the number of protons in the nucleus. For example, a carbon atom has 6 protons in its nucleus. An atom with 1 more proton, then this is a nitrogen. And an atom with 1 fewer proton is boron. Very nice. Also, the number of protons in an atom of a given element is fixed. The number of neutrons is less restricted. For instance, if you added a neutron to a carbon nucleus, it would still be carbon, but it would be slightly heavier. Atoms that have the same number of protons, but a different number of neutrons are isotopes. Carbon has 2 stable isotopes. One contains 6 protons and 6 neutrons for a total of 12 particles and is thus called carbon-12. Carbon-13 has 6 protons and 7 neutrons in its nucleus. The number of electrons in an atom of a given element can vary. Protons and neutrons are bound tightly into the nucleus, but the electrons are held loosely in the electron cloud. Running a comb through your hair creates a static charge by removing a few electrons from their atom. An atom that has lost 1 or more electrons is said to be ionized and is called an ion. A neutral carbon atom has 6 electrons to balance the positively charged of the 6 protons in its nucleus. If you ionize the atom by removing 1 or more electrons, the atom is left with a net positive charge. Under some circumstances, an atom may capture 1 or more extra electrons, giving it more negative charges than positive. Such a negatively charged atom is also considered an ion. Atoms that collide may form bonds with each other by exchanging or sharing electrons. 2 or more atoms bounding together form a molecule. Atoms do collide in stars, but the high temperature cause violent collisions that are unfavorable for chemical bonding. Only in the coolest stars are the collisions gentle enough to permit the formation of chemical bonds. You will see later that presence of molecules such as titanium oxide, TO, in a star is a clue that the star is very cool. In later lectures, you will see that molecules can form in cool gas clouds in space and in the atmospheres of a planet. So far, you have been thinking of the cloud of the whirling electrons in a general way. But now it is time to be more specific as to how the electrons behave within the cloud. Electrons are bound to the atom by the attraction between their negative charge and the positive charge on the nucleus. This attraction is known as the Coulomb force. After the French physicist Charles Augustin de Coulomb, to ionize an atom, you need a certain amount of energy to pull an electron away from the nucleus. This energy is the electron's binding energy, the energy that holds it to the atom. The size of an electron's orbit is related to the energy that binds it to the atom. If electron orbits close to the nucleus, it is tightly bound, and a large amount of energy is needed to pull it away. Consequently, its binding energy is large. An electron orbiting farther from the nucleus is held more loosely, and less energy is needed to pull it away. That means it has less binding energy. Okay? Nature permits atoms only certain amounts, quanta, of binding energy. And the laws that describe how atoms behave are called the laws of quantum mechanics. Much of this discussion of atoms is based on the laws of quantum mechanics. Because atoms can have only certain amounts of binding energy, your model atom can have orbits of only certain sizes called permitted orbits. These are like steps in a staircase. You can stand on the number 1 step or the number 2 step, but not on the number 1 and 1/4 step. Do you understand? Okay? And the electron can occupy any permitted orbit, but not orbit is between. The arrangement of permitted orbits depends primarily on the charge of the nucleus, which in turn depends on the number of protons. Consequently, each kind of element has its own pattern of permitted orbits. Let's look at this slide, please. Isotopes of the same elements have nearly the same pattern because they have the same number of protons. However, ionized atoms have orbital patterns that differ from their unionized ones, and thus the arrangement of permitted orbits differs for every kind of atom and ion. How can you understand nature if it depends on the atomic world you cannot see? You can see objects such as stars, planets, aircraft carriers, and hummingbirds, but you can't see individual atoms, right? As scientists apply the principle of cause and effect, they study the natural effects they can see and work background to find the cases. Inevitably, that gas for leads back to the invisible world of an atom. Quantum mechanics is a set of rules that describe how atoms and subatomic particles behave. On the atomic scale, particles behave in ways that seem unfamiliar. One of the principles of quantum mechanics specifies that you cannot know simultaneously the exact location and motion of particles. This is why physicists prefer to describe the electrons in an atom as if they were a cloud of negative charge surrounding the nucleus, rather than small particles following individual orbits. Do you understand? Clouds instead of individual. And this raises some serious questions about reality. Is an electron really a particle at all? If you cannot know simultaneously the position and motion of a specific particle, how can you know how it will react to a collision with a photon or another particle? The answer is that you can't know, and that seems to violate the principle of cause and effect. Many of the phenomena you can see depend on the behavior of huge number of atoms, and quantum mechanical uncertainties every show. It's very nice and fantastic, right? Nevertheless, the ultimate causes that scientists seek lie at the level of atoms. And modern physicists are trying to understand the nature of the particles that make up atoms. That is one of the most exciting frontiers of modern science. If light did not interact with matter, you would not be able to see these worlds. In fact, you would not exist because, among other problems, photosynthesis would be impossible. And there would be no grass, wheat, bread, beef, cheeseburger, or any other kind of food. The interaction of light and matter makes life possible. And it also makes it possible for you to understand the universe. You should begin your study of light and matter by considering the hydrogen atom. It is both simple and common. Roughly 90% of all atoms in the universe are namely hydrogen. Each electron orbit in an atom represents a specific amount of binding energy. So physicists commonly refer to the orbits as energy level. Using this terminology, you can say that an electron in its smallest and most tightly bound orbit, in its lowest permitted energy level, which is called the atom's ground state. You could move the electron from one energy level to another by supplying enough energy to make up the difference between the two energy levels. It would be like moving a lava core from a low shelf to a high shelf. The greater the distance between the shelves, the more energy you would need to rise the core. The amount of energy needed to move the electron is the energy difference between the two energy levels. If you move the electron from a low energy level to a high energy level, the atom becomes an excited level, an excited atom. That is, you have added energy to the atom to moving its electron. An atom can become excited by collision. If two atoms collide, one or both may have electrons knocked into a higher energy level. And this happens very commonly in hot gas, where the atom moves rapidly and collide often. Another way an atom can become excited is to absorb a photon. Only a photon with exactly the right amount of energy can move the electron from one level to another. If the photon has too much or too little energy, the atom cannot absorb it. You remember, as a quantum portion, because the energy of a photon depends on its wavelength. Only photons of certain wavelength can be absorbed by a given kind of atom. And this figure shows the lowest four energy levels of the hydrogen atom. Look, in the center, 1, nearest 2, 3, and all outer 4. The longest wavelength photon has only enough energy to excite the electrons to higher level. Atoms like humans cannot exist in an excited state forever. An excited atom is unstable and must eventually, usually within 10 in power minus 6 or 10, even 10 in power minus 9 seconds. How many times? It's less than 1 second. And given the energy it has absorbed and returned its electron to a lower energy level. And thus, the electron in an excited atom tends to tumble down to its lowest energy level, its ground state. When an electron drops from a higher to lower energy level, it moves from a loosely bound level to one that is more tightly bound. The atom then has a surplus of energy. The energy difference between the levels that it can emit as a photon. Study the sequence of events in this figure to see how an atom can absorb and emit photons. Because each type of atom or ion has its unique set of energy levels, each type absorbs and emits photons with a unique set of wavelengths. As a result, you can identify the elements in a gas by studying the characteristics wavelengths of light that are absorbed or emitted. The process of excitation and emission is a common sight in urban areas at night. A neon sign glows when atoms of neon gas in a glass tube are excited by electricity flowing through the tube. As the electrons in the electric current flow through the gas, they collide with the neon atoms and excite them. Almost immediately after a neon atom is excited, its electron drops back to a lower energy level, emitting the surplus energy as a photon of a certain wavelength. The photons emitted by excited neon blend to produce a reddish-orange glow, signs of other colors, erroneously called neon, contain other gases or mixtures of gases instead of pure neon. Whenever you look at the neon sign, you are seeing atoms absorbing and emitting energy. If you look closely at the stars in the constellation Orion, you will notice that they are not all the same color. One of your favorite stars, Betelgeuse, in the upper left corner of the Orion is quite red. Another favorite star, Rigel, in the lower right corner is blue. This difference in colors arises from the way the stars emit light. And as you learn why Betelgeuse is red and Rigel is blue, you will begin to see how astronomers can learn about stars by analyzing starlight. The starlight that you see comes from gases that make up the visible surface of the star, its photosphere. Layers of gas deeper in the star also emit light, but that light is reabsorbed before it can reach the surface. The gas above the photosphere is too thin to emit much light. The photosphere is the visible surface of a star because it is dense enough to emit lots of light, but thin enough to allow that light to escape. That's very nice, right? Stars produce their light for the same reason a heated horse core glows in a blacksmith forge. If it's not too hot, the horse core is already red. But as it heats up, it grows brighter and yellower. Yellow core is hotter than red core, but not as hot as a white core. Stars produce their light the same way, exactly the same. The light from stars and horse cores is produced by moving electrons. An electron is surrounded by an electric field. And if you disturb an electron, the change in its electric field spreads outward at the speed of light as electromagnetic radiation. Whenever you change the motion of an electron, you generate electromagnetic waves. If you run a comb through your hair, you disturb electrons in both hair and comb, producing static electricity that produces electromagnetic radiation, which you can hear as snaps and crackles if you are standing near an AM radio. Stars don't comb their hair, of course, but they're hot and they're made up of ionized gas. So there are plenty of electrons zipping around. The molecules and atoms in any object are in constant motion. And in a hot object, they are more agitated than in a cool object. You can refer to this agitation as a thermal energy. If you touch an object that contains lots of thermal energy, it will feel hot as the thermal energy flows into your finger. The flow of thermal energy is called heat. In contrast, temperature refers to the average speed of the particle. Hot cheese and hot green bean can have the same temperature, but the cheese can contain more thermal energy and can burn your tongue. Don't try. Thus, heat refers to the flow of thermal energy, and temperature refers to the intensity of the agitation among the particles. When the astronomers refer to the temperature of a star, they are talking about the temperature of the gases in the photosphere. And they express those temperatures on the Kelvin temperature scale. On this scale, 0 degrees Kelvin, written 0K, 0 Kelvin, is absolute zero. The temperature at which an object contains no thermal energy that can be extracted. Water freezes at 273 Kelvin and boils at 373 Kelvin. The Kelvin temperature scale is used in astronomy because it is based on absolute zero and consequently is related directly to the motion of the particles in an object. Now you can understand why a hot object glows. The hotter an object is, the more motion among its particles. The agitated particles collide with electrons. And when electrons are accelerated, the part of the energy is carried away as electromagnetic radiation. The radiation emitted by a heated object is called black body radiation. A name that refers to the way a perfect emitter of radiation would behave. A perfect emitter would also be a perfect absorber, and at room temperature would look black. You will often see the term black body radiation referring to objects that glow brightly. Black body radiation is quite common. In fact, it is responsible for the light emitted by an incandescent light bulb. Electricity flowing through the filament of the light bulb heats it to high temperature and it glows. You can also recognize the light emitted by a heated horse core as black body radiation. Many objects in astronomy, including stars, emit radiation approximately as if they were black bodies. That's very nice. Hot objects emit black body radiation, but so do cold objects. Ice cubes are cold, but their temperature is higher than absolute zero, so they contain some thermal energy and must emit some black body radiation. The coldest gas drifting in space has a temperature only a few degrees above absolute zero, but it too emits black body radiation. Two features of black body radiation are important. First, the hotter an object is, the more black body radiation it emits. Hot objects emit more radiation because their agitated particles collide more often and more violently with electrons. That's why a glowing coal from a fire emits more total energy than an ice cube of the same size. The second feature is the relationship between the temperature of the object and the wavelength of the photons it emits. The wavelength of the photon emitted when a particle collides with an electron depends on the violence of the collision. Only a violent collision can produce a short wavelength or high energy photon. The electrons in an object have a distribution of speed. A few travels very fast, and a few travels very slowly, but most travel at intermediate speed. The hotter the object is, the faster, on average, the electrons travel. Because high-velocity electrons are rare, extremely violent collisions don't occur very often. And short wavelength photons are rare. Do you agree with me? Nice. Similarly, most collisions are not extremely gentle. So long wavelengths or low energy photons are also rare. Consequently, black body radiation is made up of photons with a distribution of wavelengths, with medium wavelengths most common. The wavelength of maximum intensity is the wavelength most common, maximum intensity, lambda maximum, at which the object emits the most intense radiation and occurs at some intermediate wavelength. Make special note that lambda maximum does not refer to the maximum wavelength but the wavelengths of maximum. And this figure shows look at this at the bottom, the intensity of radiation versus wavelengths of these three objects of different temperature. This maximum less temperature, and this is a higher temperature. The cars are high in the middle and lower there either, and because the object emits most intensity at intermediate wavelength. The total area under each car is proportional to the total energy of emitting. So this total energy is higher than this total energy under this, right? And you can see that the hotter object emits more total energy, like in the up, than the cooler object, as you can see at the bottom, right? And look closely at the car, and you will see that the wavelength of maximum intensity depends on temperature. The hotter the object, the shorter of wavelengths of maximum intensity. The figure shows how temperature determines the color of a glowing black body. The hotter object emits more blue light than red, and thus looks blue. And the cooler object emits more red than blue and consequently looks red. Here that look more blue because it emits more blue. And this emits more red. And now you can understand why your favorite stars, Betelgeuse and Rigel, have such different colors. Betelgeuse is cool and looks red, like here at the bottom. But Rigel is a hot and looks blue. The infrared radiation coming out of your ear can tell a doctor your temperature. How does it work? You know two radiation laws, so your argument must use the right one. Doctors and nurses use a handheld device to measure body temperature. By observing the infrared radiation emerging from patient's ear, you might suspect the device depends on the Stefan Boltzmann law and measures the intensity of the infrared radiation. A person with a fever will emit more energy than a healthy person, right? However, a healthy person with a large ear canal would emit more than a person with a small ear canal. So measuring intensity would not be accurate. The device actually depends on Wien's law, in that it measures the color of the infrared radiation. A patient with a fever will emit at a slightly shorter wavelength of maximum intensity. Look at this with a higher wireless. And a patient with the infrared radiation emerges from his or her ear will be a tiny bit blue than normal. Astronomers can measure the temperatures of stars the same way. Adopt your argument for stars. Use this figure to explain how the colors of stars reveal their temperature. Okay? Next lecture will be the spectrum. I hope you enjoy this lecture, and I'm looking forward to see you next time. Okay? Bye.